Hello, welcome back. I'm sure you are learning as much as you would like to learn through the previous sessions. And we are on embedded system design. You are learning ARM Cortex M4 embedded C microcontroller programming. If you haven't done so, please go back and revise all the previous sessions. So this session would be easy for you to follow along. And also, if you are having any doubts, that will also help when you go back and revise. We are on day 27. We're going to learn day 27 the SPI what we left off from the other session, SPI part 2. Today we're going to learn about a small recap about these two, what is SPI and the SPI work. I won't go into much detail because I already explained all of that. Today we will be writing a code for the SPI transmit and the SPI receive, and also all the ADXL accelerometer functions. And finally you're going to learn how to interface it and see the value, the live expressions in the IDE. So let's go in. Before getting in, I would like to give a small introduction. I'm representing A2DG. It's a startup by Anbukarasu brothers, my brother Alex and myself Arul in 2023. Both of us gathered industry experience over 20 plus years, and we would really like to put it out there for you all so that it would be beneficial for you to make yourselves settle into a better professional. And our mission is to convey our knowledge to at least 100,000 future professionals through our online courses. And the main advantage of this is you can study from wherever you are, and that is really good about that. About me, I'm Arul P. Anbukarasu. You can call me as Arul or APA, as persistent as I would like to be to share my knowledge and experience with you. I have 20 plus years of experience working in various industries in Australia, Italy, Singapore, and in India. On these industries on renewable energy sector, that is for the solar and the wind power conversion, the power systems that related to lead acid batteries, network embedded systems that's connected to ATMs, teller cash registers and point of sale machines, banking automation systems, and the smart parking operations. And my expertise lies in these three: embedded systems, VLSI, and project management. I have a small announcement to make. I have categorized into two different categories: the YouTube viewers and internship professionals. All the videos will be uploaded to A2DG YouTube channel. In order to be eligible to get a free certificate, you have to attend and watch at least 28 videos. At the end of each and every session, there will be attendance link. Click on that and fill the details and send it across to us, and that will count for your attendance. Part of the YouTube regulations, the videos can't stay there forever, so it has to be removed after 2 or 3 days. So in case if you want to revise and if you want to go back further lessons, previous lessons, you can't, unfortunately. So for that main reason, I strongly recommend you and advise you to join in one of our internship program, which will give you the top level internship certificate, and that sits right on the top when you land for the interview or after you got the first job. When you work with the senior engineers, the amount of journey that you put through to learn this microcontroller is worth a lot, because they don't have to teach you all the fundamentals. You already learn the fundamentals, and also you going to work on, and you already going to work on projects, and that is a big plus. And they consider this as a big effort from your point of view, and you can start from day one and you will be more productive with the team. Not only that, you will have your separate login, so you can log into our LMS portal and you can go and check each and every day session, and once you finish, click on the complete button, and that will automatically take you to the attendance for that session. Not only that, you will get unlimited access to all the course contents. That includes PDF materials, the source codes, the reference manual, the data sheets, whatever you need for this course. And also unlimited course videos access. If you want to pause and if you want to go and do something, want to come back and rewatch it, you can do that. Also, you can go further back to do revision. You can also do that. It's for you to keep it. If you get stuck in the middle, please to contact our backend support team. They are a lovely, friendly team, and they would be able to help you further along in your journey with your smooth learning. So, shall we get into learn and see what today holds? I'm sure I am keen as, because we already learned the first step of the SPI initialization, and we configured all the necessary registers, and also we configured the chip select. And today we're going to learn about the SPI transmit and SPI receive, and also the ADXL interface. So let's get in and learn today. I'm not going to bore you again with all this. I'm going to brush past all of this. So I'll just flick through this. So please be patient with me, as we covered all of this in the last session. So I'm just leaving it there, so you know when you see this slide, so your mind automatically knows, okay, you learned that. So that's why I'm leaving the continuation, not to delete it. So we learned all of this yesterday or the previous session, and also we know how the shift registers work in the full duplex mode. When one data got pushed, the other data comes and fills into that bit. So likewise, the operation continues. And then 3 different form of communication: full duplex, half duplex, and simplex, and how the communication performs, and how you can transmit the data, and the timing, 3 different timings: the setup time, hold time, and propagation delay. And an example how the communication is performing, and a bit of advantages and disadvantages. And then we went straight into the SPI in STM32. When you want to act one device as a slave mode, you need to make sure the NSS work as a chip select just as an input, and this will start to communicate with the master. Whereas if you want a device to be coded into the master mode, then you can either use it as an output or an input. But if you set that as input, then there can be options of multiple master bus collisions. So to avoid that, in the master mode, you need to always set this configuration to output, so that you can start to select the signal through the chip select, and you can select which slave device you're going to communicate to. And then you learned about the slave management. It is controlled by the software. And then the functional block diagram, as we run through quickly with the read, the RX buffer and the transmit buffer, both have the shift registers. And through all these control 2 registers, you can set all the interrupts and the status registers to check the busy condition, the TXE and the RXNE. And with the control register 1, you need to set all of these bits: the clock phase, the clock polarity, master. You're going to set the bit rate, baud rate, generator, and the peripheral enable, the SPI enable. And then you need to send the master most significant bit first, and then the data frames, you're going to set that as a 8-bit data, and then the slave select and the software slave management. So these are all the bits that you need to consider in the SPI block diagram for our example and the interfacing. And then the different bus connections where that is connected, because we are using SPI 1 and SPI 1 is connected to APB2. There are also other SPIs, SPI 4, SPI 2 and 3 is connected to APB1. If you use SPI 2, then you need to use APB2, whereas we are using SPI 1, so you need to connect this APB2 peripheral, and also you need to enable the GPIO port A clock access that you learned elaborately in the previous session, and how the serial clock frequency is calculated. And then these are all the bits we already did in the SPI configuration. The control register 1, control register 2 is used for interrupts, then the status register for the status register, and the data register to read the data. And these are other SPI registers, and this is a schematic. Chip select, we used it for port A9, and STO, the MISO connected to port A6, the MOSI is connected to port A7, and the serial clock is connected to port A5. So this is where the part 2 continues. So this is about just the explanation about each and every pin. First pin is the ground, second pin is the supply voltage, the third pin is the chip select, fourth and fifth pins are used for the interrupts, then the STO pin is used for the serial data output. This can be also used for the I2C as well, but today we are learning SPI as a 4-wire. And then the SDI can also be renamed as SDI or SDI out, and we are using a SPI 4-wire, so that's a serial data input. And then the serial communication clocks, the SCL, and SCL is connected to PA5. And this is the pin description of ADXL 345, and you just saw this in the ADXL, so this is a bit elaborated pin description about the chip. As you know, it is a 3-axis accelerometer XYZ. It controls the movement detection, and also it detects and registers the data. And these are all the registers that we're going to use that's going to relate with the SPI, the data format R, power control, and these are all the hex values, the data start address, the reset address, and you're going to set and measure. So these are all the values you need to include when you use it. And then you need to interface the ADXL in 2 different modes, as a read mode and a write mode, and you're going to define the macros. So in order to distinguish between the SPI and the I2C when sending the address, the only difference here, if you use it as a SPI, you need to accommodate that with a multi-byte. But in I2C there is no multi-byte. You use the start and the stop condition. Here you're going to use the multi-byte condition. So for a SPI 4-wire write, you need to first send the write and then multi-byte immediately. For the SPI read, you need to send the read operation, and thus the value 0 cross 80, and then the most significant bit, the MB, is classified as most significant bit. So you need to use both of this operation. That's the read operation, and this is the write operation, which is the read is 80, 0 cross 80. Then the status flags, to check whether the transmit enable or to set when the flag is cleared or not. Then the RX buffer not empty, so we're going to check on the status flags on these two. Then the overrun condition flag also, you need to use the data register for a read access, and if anything is overrun, for the clearing with the status register as well. So we're going to use this flag, and then we're going to link that interface to the ADXL3. First step to interface, you need to link to the device ID, and the device ID hex is 0 cross 00, and it's a 8-bit data. Then you use a power control to measure it, and then you also reset it. So for reset, it's 0 cross 00. For power control, 0 cross 2D. And then the range settings, because we're going to set this range plus or minus 4G, so we need to set this as the 4G. So you need to set the data D1 and D0 range as 01. So the data format register controls a presentation of data register that is from 0 cross 32 to 0 cross 37. All data except that for the plus 16 clip to avoid rollover. So you will get all this from the data sheet. So you need to also download ADXL 345 and refer the data sheet from there. This is to elaborately discuss about the different ranges. The sensor has 3 axes, as you know, X, Y, Z, and the pins that can be used for both I2C and also SPI, digital interfacing. And you can set the sensitivity level, and you can choose out of these 4 ranges, plus or minus 2G, plus or minus 4G. We're going to use plus or minus 4G. plus or minus 8G and 16G, the lower the range gives more resolution for slow movement. So that's why if you want to use for slow movement capturing, then you can go for plus or minus 2G. For any other high speed tracking, you better to sit on plus or minus 4G for high speed tracking. So this is the register map of the ADXL that I was talking about. So different hex values, as you can see, the data x0 x1, y0 y1, z0 z1 is captured from 32 to 37, and the data format is from 0 cross 31. Power control we're going to use, that's on the power saving feature 0 cross 2D, and pretty much that's it. We use the device ID 0 cross 00, so that's the device ID. And this is the sensitivity, because we are using the sensitivity at the XG, YG and ZG, and we're using each axis for plus or minus 4G on a 10-bit resolution. Because to measure the sensitivity, you have to divide that by 128. If you use a plus or minus 2G 10-bit resolution, you got to divide that value by 256. But we're going to divide this by 128. I'll show that in the program when we go there. Briefly, just a recap about what we did from the previous session. We did the SPI GPIO initialization by doing all these 5 steps that I won't bore you with. And then we did the SPI config initialization already with all these steps. Again, I won't bore you with. Please review the previous session, you will learn everything. And then we also end up with chip select enable and disable. The chip select enable and the disable, we also did this. And today we're going to learn to write to interface with the ADXL. First ADXL 345 initialization, and then you're going to do the GPIO pin initialization and then SPI config. You got to call these 2 functions because we already created that. You're going to interface that. So those 2 are called first, and then the data range of plus or minus 4G. Then the step is to reset all the bits. Then you need to do for power control measure. So you need to do this power control. And then the ADXL read mode, as you remember, first you need to set the read operation, then followed by you need to do the multi-byte. Then you just enable and start to transmit the address of 1, and then read all the 6 addresses, 6 data, the x0 x1 x0 x1 y0 y1 z0 z1, and then just disable. And the ADXL write is you need to just write to 2. Data of 0 you just R with multi-byte, and this data places into the buffer. Then get that value from the buffer and read it, and you just enable and start to transmit data to this 2 pins, and then disable it. And also on top of this, we're going to learn about the SPI transmit and SPI receive as well. I'm sure you are keen as I am to get into the programming, and I will give you a couple of minutes break, so please go and enjoy that break. When you come back, I will start with the SPI transmit and SPI receive and take it from there. So I'll see you in a couple of minutes. Go and enjoy that. Until then, take care.